Hello and welcome to The Explainer. Today we're going to break down a really clever algorithm for finding the best path through, well, just about anything. A maze, a network, even a city map. It's called Best First Search. And it all kicks off with a question I guarantee you've asked yourself before.
So imagine this. You're in a city you've never been to, your phone's dead, and you need to get to that big landmark way across town. You're standing at an intersection. What do? Do you just start walking down every single street hoping you get lucky? Or do you look around and try to make a smart, educated guess about which way feels right? That choice, right there, is exactly what we're diving into today. So, here's our game plan. First, we'll talk about the basic problem every searcher faces. Then, we'll reveal the secret ingredient, the power of a really good guess. After that, we'll break down how the algorithm actually works, step by step, take it for a spin on a map, and finally, get into the really important difference between a good answer and the perfect one. Okay, let's start with that fundamental problem. When a computer needs to find a path from point A to point B, it has the exact same dilemma you do when you're lost. Does it check out every single possible route, or does it try to be a little more clever about it? These two ways of thinking have names, and they make all the difference in the world. And this slide just lays it out perfectly. On one side, you have what's called uninformed search. Think of this as pure brute force. It would literally check every single path, one by one, until it stumbles upon the goal. Yeah, it'll get there eventually, but it's going to be incredibly slow. On the other side, we've got informed search. This is like stopping to ask a local for a hint. You're using a piece of outside info to guide your decision. And best first search, it lives right here in this smarter category. So that hint you get from a local, well, it actually has a technical name, and it is the entire engine that makes this algorithm run. It's called a heuristic, and it's basically just a fancy word for a really smart guess.
At its core, a heuristic is just a smart shortcut. It's an educated guess, a rule of thumb, that lets us prioritize our choices so we don't have to check everything. Now, it doesn't promise to give you the absolute perfect answer, but it's designed to get you a pretty good one really fast. It's all about cutting through the noise. And this brings it all back to our city analogy, right? The quality of the path you find completely depends on the quality of that advice, on your heuristic. If the local points you in the right general direction, you're going to save a ton of time. But if they send you the wrong way, well, your shortcut could end up taking forever. A good heuristic is absolutely everything.
So how does Best First Search actually use this heuristic? Well, it follows a really simple and honestly a kind of greedy strategy. It always takes the path that looks best in the moment. The logic is incredibly simple when you break it down. You're at your starting point. You look at all the paths you can take right now, say to places B, C, and D. You check your heuristic for each one. Which of these seems to be the closest to your final destination? You pick that one and only that one. Then you get to your new spot and you just do it all over again. Rinse and repeat until you arrive. And this is why we call it greedy. It makes what seems like the best choice at every single step, without any regard for the long game. It doesn't stop and think, maybe this other path that looks a little worse now could lead to a massive shortcut later. Nope. It has tunnel vision. It just grabs the shiniest, best-looking option right in front of it and goes. This is what makes it fast, but as we're about to see, it comes with a price. All right, enough theory. Let's put this thing to the test on an actual map and watch how it thinks. We're going to follow along and make the exact same choices the algorithm would make. Okay, here's the setup. We need to get from city A all the way over to city G. Now, pay close attention because you'll see two kinds of numbers here. The numbers on the paths are the actual travel costs. But here's the key. The algorithm completely ignores those for now. It only cares about one thing, the heuristic value. That number next to each city, that's our best guess of how far it is from our goal G. So we're starting at A. The algorithm looks around and sees three choices. We can go to B with a heuristic guess of 32, C with a guess of 25, or D, which is at 35. So what does it do? It's a no-brainer for our greedy algorithm. It picks C. Why? Because 25 is the lowest number, and a lower number looks closer to the goal. It doesn't even bother with B or D right now. It just follows its best guess and moves right on to city C. All right, now we're at C, and the process just repeats. It looks at its new options. It can either go to E with a heuristic of 19 or to F with a heuristic of 17. And once again, the greedy choice is obvious. 17 is lower than 19, so the algorithm immediately commits to path F, totally convinced it's on the fastest track to the finish line.
And look at that, there's only one place left to go, our final destination, G. And the heuristic at G is 0, of course, because, well, we're there. The search is over.
And there you have it. Path found, A to C to F to G. I mean, look how efficient that was. It only had to explore a couple of spots to find a complete path. It didn't waste any time checking out those other routes from B or D. It seems like a huge success, right?
Well, here's where things get really interesting. The algorithm was fast, and yeah, it found a path. But was it the best path? This is where the whole greedy thing comes back to bite us, revealing a hidden catch.
So let's look at the actual cost of the path it found. Now we ignore the heuristic and we add up the real travel costs on the paths we took. The trip from A to C was 14, from C to F was 10, and from F to G was 20. Add them all up and you get a total travel cost of 44. Okay, but what did the algorithm miss? Think back to when we were at city C. It had a choice between E, with its heuristic of 19, and F, with 17. Because it's greedy, it chose F, since 17 looked better. It never went back to explore E. But what would have happened if it did?
If we actually calculate the cost of this other route, A to C, then to E, then H, then G, we get a total cost of 41. Whoa, that path is actually shorter. So our algorithm found a good solution, and it found it fast, but it missed the optimal one, because its greedy focus on the immediate best guess blinded it to a better long-term route. So let's just sum it all up. On the plus side, best first search is incredibly fast and usually way more efficient than searching blindly. And its simple, greedy logic is pretty easy to code. But the downsides are huge. It's not optimal. It will give you a good answer, not always the best one, and its performance is totally at the mercy of its heuristic. A bad guess can send it way off track. And all this leaves us with a final, really big question that goes way beyond just this one algorithm. Think about a GPS rerouting you in traffic, or a video game character finding its way across a map. In all those situations, and even in our own lives, when do we choose speed over perfection? When is a fast, good enough answer actually better than a slow, perfect one? That's the essential trade-off that an algorithm like Best First Search forces us to think about.